Hi, my name is Yun. This summer project aims to develop a tool to extract and summarize data from randomized controlled trial literature. Well, systematic reviews of clinical trials are the foundation for the practice of evidence-based medicine. However, manually extracting data from clinical trial results is time-consuming and laborious. Therefore, we develop an NLP pipeline that can take the content of clinical trial literature as input and output a table with summarized results after identifying information in the text. There are two key critical tasks for the system. The first one is name entity recognition, followed by identifying the relationships between the entity pairs. So, training and evaluating the performance of these two components is the primary goal of this project. Here is an overview of the system design architecture. It is performed in three-phase tasks: data collection and annotation, model training, and system integration. First, RCT abstracts from PubMed were retrieved to develop an extensive corpus, including all common representations of results with fine-grained entity and relation labels. Next, bidirectional transformers, BUT, was used to develop our two deep neural network models for name entity recognitions and relation extraction, also as the core of the joint extraction pipeline in our system. Finally, the models with better overall performance are selected and incorporated into our system, with a synthesizer at the beginning and data integration component at the end of the system. Well, the requirements are also divided into three sections accordingly. First, in the data collection and annotation part, we collected sentence samples with various result representations, such as measures, statistical results, or textual descriptions from RCT abstracts. There are two main data sources. The first one is the gold standard corpus provided by a previous study, which contains result sentences with mainly numeric data. They are already partially labeled. The second, to create a descriptive corpus, we also collected sentences containing textual descriptions of the results from PubMed. A collection of functions were built for splitting retrieved abstracts into sentences and processing them for annotation with Prodigy. They can all be found in the data collection component. For the annotation work, 7 entity labels are given to represent interventions, outcomes, measures, comparative statistics, confidence intervals, p-values, and descriptive results. The relationship between result entities and their respective interventions or outcomes are also labeled separately. The final corpus, with fine-grained result annotations used to train and evaluate the models, includes 729 result sentences with 4,590 entities and 4,372 relation labels. The second part is model training. We use BioBERT, a pre-trained, domain-specific transformer-based model for biomedical language representations, was used to develop two deep neural network models. First, for the NER model architecture, BioBERT is set at the beginning of the pipeline as the embedding layer and gives contextual embeddings. The second component is the listening layer, the entity recognizer, which is a transition-based component that identifies non-overlapping spans of tokens. During the iterative training process, the entity predictions are compared against reference annotations to estimate the gradient of the loss, which were then passed back through backpropagation for fine-tuning the model to our entity recognition task in RCT abstracts. Details of model configuration and the hyperparameters for NER model training can be seen in the configuration file, which is also included in the appendix. For the RE model architecture, the first half is similar to the NER pipeline, followed by a relation extractor. The relation extractor then takes the entity factor as input and creates tensors of entity pairs. Finally, after outputting the probability matrix for each entity pair, the relation predictions with the highest probability are accepted. Details of model configuration and the hyperparameters for RE model training can also be seen in the configuration file. Finally, after further evaluations on the NER and RE models trained on different corpora, the models with better overall performance are selected as the two key components of our final system. The evaluation results for both models, including the performance of individual label classifications, are detailed in the evaluation section of the report. The final system starts with a synthesizer, splitting the input text into sentences. After entity recognition and relation extraction for each sentence sequentially, the data integration component interprets the entity pair predictions and assigns them to the corresponding cells of the summary table based on the dependencies. The function for data integration and tabulation can be found in the tabulate Python file. Finally, we use Streamlit to demonstrate and test our system. Let's take an abstract as an example. Copy the results section and paste it into the input field. After the system predicts entities and relationships for each sentence, we get a summary table. We can also download the CSV file as needed. Well, that's what the output file looks like. That's a wrap. Thank you for your time. Hope you enjoy it.